Welcome to Systems Philosophy. In this episode, I'm going to focus on the abstraction of the search algorithm. I've talked about it a lot in terms of evolution being a search algorithm, and in my opinion, it is the original search algorithm, the prototype of all other search algorithms. Algorithm is cybernetic speak for a series of instructions, a defined procedure. So what we have is we have a defined procedure that searches. Precisely what do we mean by that? Evolution searches reality for bodies, behavior, and relationships that survive, that harvest energy, reproduce, feed themselves, are fed on, and prey, are preyed upon. All of the things that life does. In search terms, we call those the goals, the things that we're looking for, the holy grail, if you like. In some ways, the search landscape is pictured as a geography. That might be strange to anyone who hasn't come across some of the information systems or cybernetic concepts. Let me try and explain it as simply as I can. You might be searching for the most slippery form for a car so that it's fuel efficient. That gives you a clear goal, make it aerodynamic. However, to achieve that goal, you might have certain variables, certain things that you can change. The tyre diameter, for instance, the width between the axles, the overall length and height of the car, the width of the car. The speed range for which you're trying to design, what else? I mean, that's quite a few things. I'm sure I can think of another half dozen if I go on. The number of doors, whether or not you have to have mirrors that stick out at a certain angle. So there's all sorts of things that go into designing an aerodynamic car. The cost, there's another one. Also, the market consumer appeal. Is it a high ground clearance, for instance, a sports utility vehicle, a ute, a utility? Or is it a sports car or a family car or a station wagon? Anyway, I've made my point. So what we have is we have very good physics around aerodynamics. And so what we can do is we can program an aerodynamic simulator model, and we can set up a design architecture much like CAD, computer-aided design, to put a 3D model inside one of these physics simulators, much like within a game engine, but this one is specifically designed to measure aerodynamic forces. We used to do that manually in wind tunnels. Now we do it what's called in silico, so we do it in silicon in computers. But the same thing used to be done. You would get a design, carve it out of clay or wood, put it in a wind tunnel. You would have force measurement devices, and then you would graph the forces on your little model at various wind speeds and angles, and then come up with some sort of understanding of how well or how aerodynamic your vehicle is. That's a slow type of search, but it's still quicker than building a whole car and checking the aerodynamics. All you need to do is build the model. Now that we can 3D print models, you don't even need the manual process of carving them. You can simply 3D print one, measure test it, 3D print another, measure test it. So what we have is we have an example of a search algorithm that is trying to find a better aerodynamic car shape. We have the physical forms that search algorithm takes, the carved wax or timber model in the windscreen, maybe the original test of just building the car or full-size mock-up, down to a scale model and a wind tunnel, and then over to various forms of computer model configuration. So not only has the search for the physical form discovered a better physical form, the method of search itself, the meta search, the search of the search space, is also changing. And that is the sort of thing that systems philosophy highlights. It gives you the paradigm that we can have a search for a particular optimum or group of optimums, and we can also have the search for better search mechanisms, be it trialing in the real world or be it building models of the search. In cybernetics, we have also developed a novel type of search called an evolutionary algorithm. What this search does is it varies the form slightly. So in the term of car models, an engineer or a designer designs what they think will be a slick and marketable car. You test the design and then you have a figure for how much fuel economy you expect to go into wind resistance. And if it's a city car, you might not care that much. If it's something that's going to do a lot of highway cruising, and particularly in a market where fuel economy is important, then you might give the aerodynamics a certain weight amongst the other aesthetics of your overall search for the perfect form, be that what the marketplace wants, what it costs you to build. So what I've also showing you now is that the search can have one particular focus, but the focus itself is also nested inside other focuses. How much does it cost to build? How easy is it to build? How easy is it to repair if we're sticking with the car? How much do people like it? How easy is it to recycle? What sort of materials does it use? What sort of manufacturing breakthroughs can we leverage to perhaps improve or get into design spaces that have been closed to us? In this way, technology and our search through the technological space of possibility echoes biology and its search through the biological space of what life forms can do, what form they can take, what structure, what lifestyle, what lifespan. From that perspective, search is ubiquitous. I'm trying to focus today on the technical space so that we can see the same sort of dynamics that evolutionary biologists noted, and especially Charles Darwin, where he was looking at the various related forms and came up with a plausible mechanism that allowed for the drift in the dynamic equilibrium of a species to speciate. For instance, he saw that a common bird, the finch, found its way to an isolated ecology, the Galapagos Islands. And in that ecology, it found ecological niches that had not been exploited. What that allowed, it allowed the form of the finch, which was well adapted to its existing ecological niche, to explore and expand its habitat, its food preferences, and therefore increase its variability. And ultimately, because too much variability starts to become maladaptive, what we get is we get speciation. We get that one original finch. However it got to the Galapagos Islands, it might have been a small population drifting on a... You can get floods washing small floating islands out to sea. It can be just a fertile female that laid some eggs and that seeded the population. I can't say. But somehow a species went from one ecology to another that had not come across that species before. The species over time expanded the search algorithm for its own fitness landscape because it was no longer hemmed in by competing species in its ecological niche. And over time, the variability became such that it made sense for certain specialists to begin speciating. It might be things like microhabitats or microclimates or individual island ecologies. So islands provide a clear niche separation. The finch might be capable of flying from island to island in extreme cases, but it may not. And each island might have slightly different ecology and habitat. And that itself is a force that can lead to different drift in the dynamic equilibrium. So the species might remain the finch, but over thousands or tens of thousands of years, what you see as an ecologist that doesn't use genetics to determine species, but physical characteristics, which was what biology did for most of the taxonomy in the tree of life. It had to try and classify based on appearance. What you see is different species, different body shapes, different beak shapes as specialization shifts. And so the genetic search algorithm, just like the designer searching for the optimum consumer vehicle, has explored different forms, and the dynamic equilibrium has dragged its gene pool along with it. Now, those Galapagos finches could have interbred with the other finches on the different islands. So at some stage, we didn't have yet a separate species, we had a subspecies. Given enough time, though, the drift accumulates enough mutations to make reproduction dicey. You might get hybrids. Maybe those hybrids become fertile, in which case what you're doing then is rebridging to isolated populations to allow a form of gene flow across them. So ideas can bridge between one species and another in the gene pool. It might also finally lead to those two species diverging to the point where they only produce sterile offspring, in which case the hybridization will not be something that happens except for perhaps in extreme need, because the dynamics don't favour it. Okay, back. So the genetic search algorithm is a slow drift, variation of form, that then over time changes the design. And there's a famous case where the principles of a genetic search were applied to cybernetics. Radio antennas follow well understood rules of electromagnetic dynamics, Maxwell's equations, amongst other things. And so if you design a radio antenna to transmit and receive, you usually design for things like the frequency spectrum that you're going to transmit and receive over, the gain, so the sort of amount of noise that the antenna can tolerate, because there is always background noise in the electromagnetic spectrum, including the radio spectrum, and the directionality of the antenna. Do you want a general antenna that can scan a wide field without having to be sort of directly focused, or do you want something specific like a radio dish for a space telescope? Okay. When we first started putting antennas into space on satellites and on orbiting capsules, we discovered, the collective, we as humanity engineers, discovered that antennas on the Earth have their vibration frequency dampened through things like atmospheric air resistance. In space, in a vacuum, any small frequency doesn't get dampened, and you can get things like harmonics building up in certain designs. They can lead to direct failure, and they can also lead to vibrations that either interfere with the transmission itself or induce stress at certain points within the antenna structure that lead to premature metal failure through fatigue. None of these things are good when it comes to designing satellites that are meant to transmit and receive communication over years, if not decades, without maintenance. So, the idea of an evolutionary algorithm was put into the problem of engineering a better antenna. What they did is they built a simulator that simulates harmonics in space, and also a design program that takes a design and varies that design slightly, perhaps putting more elements on the antenna, more sub-elements, varying the length or the thickness of the individual elements, and then testing the design against specific criteria in terms of can it transmit and receive well enough to do the job. And this is where the search algorithm in software really starts to become much closer to the way that evolution searches. They set the algorithm loose, and what the algorithm designed was what no engineer would have designed. It was this really strange looking three-dimensional structure that looked chaotic, like a child had tried to design an antenna by just sticking parts together. But the antenna met the technical specifications, and more importantly, it didn't suffer from the runaway harmonic dynamics. It was able to damp vibrations even without atmosphere. This is a field of science called biomimicry. In this case, we haven't just mimicked bird wings when we're trying to fly. We have mimicked nature's search algorithms when we try to design. All of this is encapsulated in systems theory, because the system that tests the design, the system that models reality, the system that varies the design. These are all information systems that are human designed and in some cases design in ways that humans now cannot. The same is happening in the fields of artificial intelligence. More and more software is not just being used to design better computer chips, to build better programs and design better algorithms. Software is designing software, and software is now also beginning to design better ways of designing software. That's the meta-design process that I talked about with the antenna and with life. This is important in concepts such as artificial intelligence because suddenly we introduce a new dynamic. They talk about the progress flywheel with artificial intelligence. The progress is getting quicker. More money is flowing into artificial intelligence, which is building bigger individual models. It's putting more talent into artificial intelligence. It's dedicating more compute to artificial intelligence. It's focusing more research into building better chips, building better memory, building faster architectures. And now what it's doing is it's focusing the intelligence itself on building better ways to build intelligence. This is an exponential improvement in search that is the ultimate endpoint of the stack of concepts that I'm building towards, and a little bit of a taster in this episode that I've dedicated to the concept of the search algorithm. The fact that search can be long and drawn out. It involves phase changes. For instance, there was a long search in writing and paper technology until finally we invented a printing press. And then we had better technology, which then led to better dissemination of knowledge. The abstraction here is when I'm talking about complex dynamic equilibrium systems. The dynamic equilibrium means that there are forces trying to disrupt the system, to introduce chaos and variability. There are forces that are stabilizing the system, that are bringing the system back from the edge of chaos, so that when a body lifts weights that don't destroy the skeletal muscles or the skeleton itself, the body can repair and even make those muscles stronger. That's the concept of anti-fragile dynamic equilibrium. We get the same process with our technology. When a ship rips a sail, we replace it with a sail. When a car has a flat tire, we repair that flat tire. The dynamic equilibrium between entropy, the normal degradation of the technological forms that we build, and repair, the interventions we take, so the order and the chaos, continues into our technology. That dynamic equilibrium undergoes slow evolution in technology through the search space, and you can see that if you track the form of the earliest cars into each different generation. Technology undergoes a small, from our perspective, a slow drift as each generation of car is released and refined. So model by model, the entire global range of cars undergoes a sort of dynamic equilibrium drift. It is also part of the technological search, looking for more fuel efficient cars, utilising materials better, and simply the drift of cultural preferences and the general drift of society and technology. Search is one paradigm, one framing of the reality that is reality, the thing that cannot be separated from itself because it is itself. We frame it because the framing allows us a module, a map from which to understand it simply, like a little thought experiment or series of thought experiments or scientific theory that gives us deeper insight into a particular phenomenon. So one of those framings, paradigms, perspectives is dynamic equilibrium. The drift of that dynamic equilibrium over time, and then the forces that try to disrupt that drift and also restabilize that drift. And that process of dynamic equilibrium drifting, becoming stabilized and disrupted, can be characterized as a sort of genetic search algorithm, a evolutionary search algorithm. You can frame it in many ways, and which is why I spent today's episode focusing specifically on the concept of search. Thank you for your attention. This is Systems Philosophy.